said it again clearly. If you look at the top dimensional cohomology, so hd of x, where d is the dimension of x, then this is generated. This is just z. It's just generated by the class of any point, because remember x here is always a smooth algebraic complex variety, syntactically it's connected, so every point has the same class. So that means the top homology, or on the contrary, if you like, the bottom homology h0 is just generated by the class of a point, and therefore you have a natural. Right, so this I'm not writing again on the board because I'll just read what's here, and then once we get to the part where we stop, I'll start writing on the board again. Anyway, so now I'm just reading again what I was talking about last time. Right, and so I said, so there's a natural map, which is when you have this space X, you just take the map denoted pi, which, yeah, this is all on written right here, which sends X to a point, and that map, by definition, is a map, induces a push forward, which goes from h star of X to h star h star of X to h star of a point, which is just Z, and that's just the map that extracts the coefficient of the class of a point. And so that's the pairing that I was trying to explain last time. Now, if you assume that h star of X has no torsion, which will always be the case in our setting, then you have a natural pairing, which is just you take two classes, you take their product, and then you extract the coefficient of the class of a point. So in other words, geometrically, what you're doing is you're taking a representative from A or generic representative from B, you're intersecting them, and you're just counting the number of points you get in the intersection. And that's your perfect pairing between hi of X and hg minus I of X. And that's, if you like, Poincare duality, one form of Poincare duality. And since, by definition, we had defined hg minus I of X to be h I of X, h, in other words, I had defined cohomology in terms of homology. If you combine these two things together, you recover the usual duality between homology and cohomology, namely that h superscript I of X is the dual of h lower script I of X. So that was the comment I was trying to make last time, which would be confusing. And I also mentioned the fact that this product is this pairing is compatible with the product. Obviously, since you're just taking the product of the left-hand side and the right-hand side, you might as well say, if you take three of them, you can combine them. You can recombine them any way you like. You can write AB scalar product with C is the same as a scalar product with EC or any other combination that you like. All right, so this is where I stopped last time. So I had one more completely general thing I want to say about homology and cohomology. In the same way that in homology we have push forwards, in cohomology we have pullbacks. And again, with my sort of trivial definition of cohomology as being just homology with reverse grading, or if you prefer using this Poincare duality as being the dual of homology, then you can just define pullbacks as just being the dual map. So in the sense of usual linear algebra duality, if you like. So in other words, so F upper script, little star, which is the pullback, is just the map now which goes on the contrary from the cohomology of Y to the cohomology of X. Oh yeah, I was supposed to start writing again. Sorry. Right. Okay, so yeah, so one last generality, which is notion of pullback, and this is just so when you have a map F from X to Y, then you have a pullback F star of H star of Y to H star of X, and that makes cohomology a contravariant functor as opposed to homology, which is a covariant functor. And here in my stupid definition is just to say that I take the transpose map of the push forward. And the important thing here is this is a graded ring morphism as opposed to push forward, which is not it. So remember we had this ring structure we haven't talked much about yet on cohomology, graded ring structure, and pullbacks are graded ring morphisms. All right, and then we had some fun with the Riemann 2-4, which is my favorite example because that's the only one I can visualize, which is not just like projective space, let's say. Oh yeah, right. So let me close this. So in fact, yeah. So we'll get back to the computer. But so in other words, one thing we established is the fact that there is a natural basis as a graded Z module, if you like, of the cohomology of the Grassmannian, which is given by these Schubert varieties, and we worked it out in the case of GR24, and there are exactly 6 of them. And they're indexed by Young diagrams sitting inside a 2x2 square. And to remind you, especially for those that were not there, these are the 6 of them. They're naturally graded. This has degree 0. This has degree. So let me just write once and for all 2 times 1, 2, 2, 3, and 4. So this is the grading of these different objects as generators of your grading module. And obviously the grading is just a number of boxes. And again, the real grading is multiplied by 2 because there's always this issue of complex versus real two-dimension, but I can't be bothered multiplying everything by 2. And so in principle, you're supposed to have this gradient ring structure, which means, for example, when you take, so we've also established the fact that the top, the degree 0 bit is always the unit of the ring. So that means when you multiply anything by this thing, which is 1, you get the same thing. So this is a multiplication table that I was doing just as a warming up before you arrived. So this one it's just the unit. But then, for example, the second one, which is the one box Schubert variety, well, Schubert class, when you multiply it by other classes, well, you have to have some product rule which is compatible with the grading. So, for example, 1 box times 1 box is the sum of 2 terms. And in fact, this is, by the way, the only non-trivial decomposition in this whole picture, in this case, which is this one. And then there are a bunch of other cases, and of course there's a bunch of zeros which are just induced by the fact that ultimately the degree stops at 4. So if you have anything of degree more than 4, it has to be 0. So this is your multiplication table, and I also circled in blue the ones. Oh yeah. So the top dimensional. The top codimension part is just the class of the point. That's the full 2x2 rectangle. And I've circled in this table when you have products that actually produce a point. So these are the ones for which you have an interesting pairing. In fact, let me also circle this one. So I circled in blue all the things that potentially could give a point when you intersect them together. That means these are the cases where the sum of codimension equals 4. And so in principle, if you intersect them, you should, generically you should get a certain number of points. And indeed, you find on this table this thing. So how about we check a few cases by hand? It's just, again, as warming up before we actually start the talk. So unfortunately, for some reason, this doesn't even fit on the screen. I made the picture too big. So I remind you, this is just a pretty picture of a way of building geometrically Schubert classes in GR24. You have a flag, which is made of a point, a line, and a plane, and you're supposed to look at things which have a particular, so for example, we established, and also we had this other indexation of Young diagrams in terms of the places where it goes up. So for example, this one is supposed to be 1, 3, this was 2, 3, this was, and we, hopefully by now everything is correct. No, sorry, 2, 3, no. Yeah, I'll get it wrong again. This is 1, 4, this is 2, 3, this is 2, 4, and this is 3, 4, and this is 1, 2. So we have another indexation of the Young diagrams as just subsets of cardinality 2 out of 4. And for example, we decided, we found, the computer told us that the Schubert class corresponding to 2, 3 is you fix some point, and then you take all the lines going through that point, for example. So now the question is, when you want to do the product, well, so how about I remove the, let me just keep the point only, because this is the only relevant information for this flag. How about we take another flag, which hopefully is just has completely different position of the point, the line, and we take another 2, 3. So let's also just take the point. So just another point, and then we, so let's reset. So now we have just 2 points, and we're asking lines that go through two points. And the computer tells us there's exactly one line that goes through 2 points. Okay, you may wonder why you need a computer to figure this out. I agree in this case it's kind of trivial, but we're happy, and we find that indeed 2, 3 times 2, 3 equals 1. 1 times the class of the point, which is, good enough. Okay, okay, fine. So this is, sorry about that. It's a bit of a, sorry. Technical problem. Failure. Sorry, this is mathematically spring up. I don't know what happened. We'll just, sorry. But now, of course, the picture is very small and very difficult to see. Yeah, so anyway, as usual, this is a bit improvised, so things not working as we should. And then you say, what about position 1, 4 with 1, 4? And this one, so what is 1, 4? I forgot. So let's ask first the computer what 1, 4 is about. And we'll stop at this other example. Oh yeah, so these are all the lines inside a plane. So let's forget about, so now how about we have 2 planes, and we ask about lines which lie inside 2 planes, and surprise, there's only one intersection of the planes. Okay, that's kind of stupid, fine. So these two are kind of trivial. And then you could also ask for the hybrid one. You know, what about? Okay, there's really something really screwing up each time I'm doing this. Sorry about that. And we'll once again restart the program and rescale it. And then you can ask for the hybrid one. So what about 2, 3 times 1, 4, and I know I said 1, 3 times. Okay, that doesn't work. So let's 2, 3. Where's 2, 3 here? And the computer says there's nothing. And indeed, that means there are no lines that are inside a plane and go through a point which happens not to be inside this plane generically. So yeah, that's a 0 line, and so on, right? And so that was actually a point to all that I explained here, which was that you realize that there's a simple pattern here. On each row, there's exactly one. So, for example, if you have the first row, you see there's exactly one place where you get the class of the point. Here, here, here. So it means, in other words, you have a simple relation of this form, that if you compute the class of I times the class of another Schubert class, the answer is always of the form delta I j star, where star is a certain involution, right? So, for example, the empty diagram is paired with the full one. The one box is paired with the 3 boxes. The 2 boxes is paired with itself. The 2 of them, these are all self-dual, and so on, right? And so the only question is, what is this involution here? And I suppose this example, of course, is a bit small, but if you think about it for a sec, here's the recipe. You take the complement, and then you rotate it, complement of the Young diagram, and you rotate it 180 degrees. And so this is sort of important because we'll need all the time. So this is a very convenient trick, by the way, because it allows you to basically, dualize. So in other words, what I'm saying is that the basis, the Schubert basis is not, it's not an orthogonal basis. However, it's kind of globally self-dual. So the dual of the basis of Schubert classes is the basis of Schubert classes, but indexed by the diagram rotated 180 degrees and complemented. And so just for fun, one last exercise with the computer before we go to serious things. So how about we ask more complicated questions? So for example, yeah, I don't know why this never works. No, this is fine. Right. No, these are just the flags. Yeah, I'm relearning how to use my program. So for example, there's a classical question in Schubert calculus, which is the following. When you have 4 given lines in a 3-dimensional space, in generic positions, how many lines are there that intersect these 4 lines? Right, so 4 lines, so actually let me draw them for you. These will be the lines of my flag, so 1 line, 2 line, the computer has carefully selected randomly, and the 4th line, right, so these are 4 lines, and the question is how many lines go through all 4 of them? Anybody has a guess? I'm sure some of you know the answer, obviously, but so how are we supposed to compute it using this table? Well, this is nothing but computing pi star of the class of 1 box. 1 box means going through a line, and then you take it to the power 4, which means you do it 4 times, 4 different generic lines which are supposed to intersect, right? And we can do it, for example, by noticing that this is nothing but pi star of s plus s squared. I use the first time the multiplication rule, and then so this is nothing than the scalar product of this thing with itself. But then I noticed that these 2 happen to be orthogonal to each other and of a square norm 1, so that means that should be 2, right? 1 plus 1, because they're orthonormal vectors. These 2 happen to be self-dual because their diagram is invariant by rotation 180 degrees and complement. So let's ask the computer. Big suspense here. And nothing happens. Okay, that can't be right. Because I forgot, I forgot to actually select the, right. Sorry, 1, 3 everywhere. And yes, there are 2 lines going through. These are the 2 white lines. So, but let's redo this in slow motion here so we can all appreciate it. Yeah, here we go. Yeah, there are indeed 2 lines that go through the 4 lines. That's kind of a cool configuration. All right. Okay, end of the recreational mathematics session. Back to business. So yeah, I hadn't quite finished last time, the first part of the lecture, and what was left? In fact, I'll cheat and just look at my notes, because since I wrote notes for the first part, might as well use them. If I can find where is the... yeah, right. More example in GR24. Yes, we've done that. Check. And the fact that, yes, this. Okay, so we only need one more thing, which is the actual presentation. So I haven't told you yet, basically, so how to actually do this, this graded array explicitly, right? So here you could try it by hand, by the way, by saying, you could try in this case, for example, to build a presentation of this ring by saying, okay, so maybe I'm going to call. So you could try, for example, here for n equals. One last word about our favorite example. You could say, for example, maybe I'll call. The first generator would be the class of the box, and then you would have maybe that's enough to generate everything, but not quite, because E1 squared is already the sum of two terms, and you want them each of them separately. So maybe you say, okay, so how about I give another name to this one?
Yes.
And now it's okay, because this one can be expressed as E1 squared minus E2. But then you run into trouble, because when you compute already the third degree terms, you already have E1 cube and also E1, E2. And there's only really one term of degree 3, which is this one. So these two have to satisfy some linear equation. The coefficients I'll let you figure out in exercise. And you do it the same in degree 4. You'll also have an equation in degree 4, which says that this, alpha prime plus beta prime, E1 squared E2 plus gamma prime E2 squared equals 0. And probably even, no, one equation, that's enough. And then you're done. And then, so you find a presentation in terms of two generators, and in this case, two equations. And it doesn't look particularly promising, so let me give you the general recipe. Okay, so this is the other fact that I shall not prove, and then we'll move on to the second lecture, so to speak. Okay, so fact. H star gr nk. So there are two different ways I'm going to present it. The first way is more or less what I did here. I'm going to say it's the polynomial ring in k variables divided by some ideal, but I'm actually going to tell you what the ideal is, might as well. Yeah, in fact, and so the degree of EI is going to be 2i, and again, the 2 is always this conventional factor of 2 for the real dimension. And the ideal I write as follows. So I have a reason for writing it in sort of a weird way, and here it is. At first, I do the generating series of these EIs, EI t to the I, 1 to k, and then I think of this as being a formal power series in T, and I invert it. So in principle, this is a formal power series, and I claim that this series actually terminates at order, so it's a polynomial of degree n minus k in T. So in other words, I'm saying if you extend this thing, any higher order should be 0. And these are the relations in your ring. Yeah, let me not yet comment on why this is a good way to write things. So of course, in principle, you have an infinite number of relations, but there's only a finite number. Any ideal has only a finite number of generators. So in practice, you only have a finite number of them. So for example, what did we discuss before? Oh yeah, Pn minus 1. So Pn, but let me write it as Pn minus 1, which is gr. Sorry, screwed up. Kn, sorry. So this is gr1n. So in this case, you only have one generator. Let's see, how does it work? So you have 1 plus E1t inverse, which is nothing but the sum of whatever, minus 1 to the k, E1k, tk. And you're asking for this to be a polynomial of degree n minus 1, which means in particular the nth term should be 0, and that means E1 to the nth equals 0. And that's enough to generate everybody else, because then all the higher powers are also 0, and you recover the fact that your homology is z of, well, in this case, E1 divided by the ideal E1 to the nth. And that's the formula we had obtained, maybe with slightly different notations last time. All right. Yeah, again, so sketch of proof. So I'm not going to prove this thing, but for those that are slightly more familiar with the geometry, here's the really quick sketch of proof, at least the idea of it. And the first thing is to decide what is EI. So EI is pretty much what you already guessed in this particular example. EI is precisely the element is the one corresponding to the Schubert class corresponding to just one column of size I. And the relation is basically due to the fact that secretly it's something else. It's also equal to the, so that's the part I'm not going to explain, but this is also the ith Chern class of the topological vector model over over GRKN. So GRKN has a sort of obvious topological bundle in which above each point you give the space itself. So each point, remember, a point inside GRKN is actually itself a vector space. So you can above each point you could put itself basically. That's the topological bundle, right? And then there is a obvious exact sequence which says that you can always embed. So this space is always embedded inside Cn. So it has a corresponding exact sequence of vector models, which just says that, well, yeah, this is injective and this is subjective, yeah. And this equation is basically just writing the fact that the total Chern class of V times the total Chern class of Cn minus V over V is equal to the total Chern class of the thing in the middle, which is trivial. This is the trivial vector model over each point, which is just Cn. So this should be 1, C-A-T-V. And this is the total Chern class. That means the generating series of the Chern classes. And so if you just divide by, you put it on the other side, you get exactly this equation. So there's some kind of justification for this equation coming from. So of course you have to check that this is the only relation that that indeed the cohomology is generated by these classes. So that there's a lot to prove, obviously, but this is just the sketch of proof. Okay, so we're almost done with this. So I still want to say a few things about symmetric functions, because I haven't even talked about symmetric functions yet. So maybe I should say at least something, an announcement of why this has anything to do with symmetric functions. Of course, a lot of you know that secretly these are elementary symmetric polynomials. So this is the connection to symmetric functions. And we'll come back, of course, once we do the integral system, we'll come back to symmetric functions. But for now, here's how it goes. The statements first is that instead of thinking of this, polynomial in these variables E1 up to Ek with this funny grading, the degree of I is like I or 2I. How about we replace this with a normal? So how do I denote it? Yeah, I use the letters Y rather than I, rather than X for some reason. Yes, so I'm going to do the following. I'm going to say, how about right here, so here's the degree of EI was 2I, and here the degree of YI is just 1 or 2. And so the idea is quite simple. You can, any symmetric polynomial can be expanded in elementary symmetric polynomials. So the correspondence between the two is just the fact that EI will be EI will be the sum over A1 less than then less AY, AI of the Y, A1 Y, AI. Does that make sense? Elementary symmetric polynomials, yeah? And so is this statement correct then? I believe this is a true statement. Yes. Right. And for free, of course, you can rewrite this equation slightly differently, because now the generating series, of course, of the elementary symmetric polynomials is nothing but, so 1 plus sum of EI to I is nothing but product of 1 plus TY I for my state. So the equation looks a little bit nicer for the ideal. And by the way, these so so there's a geometric justification for the introduction of these things, and they usually call the Chern roots. This is a so-called splitting principle. But just as a bit of a foretaste of integrable systems, these will be exactly beta roots in the integrable system. So here we have already beta roots appearing out of nowhere. And these, of course, will be nothing but beta equations in these guys, or more precisely the TQ relation. All right. So far, so good. So we wrote this as now not polynomials, but so this means symmetric polynomials, right? It's symmetric in the exchange of the variables. So we managed to write everything as a quotient of the symmetric space of symmetric polynomials. One can do a little bit better, and this is where these symmetric functions arise. And this I may or may not have time to get back to. Oh yeah, this I think we can erase. This was very interesting. But yeah, so I may or may not have time to go back to this story of symmetric functions rather than symmetric polynomials. But there is a slight improvement you can say, which is as follows. So what is a symmetric function? Maybe you guys are not familiar with this terminology. So a symmetric function is actually, so one way you can define it, so morally speaking, it's a symmetric polynomial in an arbitrary, an infinite number of variables, an arbitrary number of variables. But one way you can define it is a sequence of symmetric polynomials. So this is a definition. Symmetric polynomials. P n of x1, so okay, y1, yn, let me use the same notations. Pk maybe, yeah, pk of 1, yk. And in your, with coefficients in your favorite ring, let me say in this case z of y1, yk, let's say, it doesn't matter, it could be any base ring, such that, where k is an integer, such that pk of y1, symmetric, y1, yk, yk minus 1, 0 is pk minus 1. So the idea is you can have as many variable as you want, but if you set 1 equal to 0, it's like it's not there, basically. So, and you see that very naturally, the things that occur here, for example, we had E1, you see very naturally these polynomials that occur in this way. For example, we had E1 that was y1 plus dot 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 plus yk. Clearly, this can be made into a sequence for any k which satisfies this property, right? So for all k, satisfies this property that if you set a variable to 0, you get back to the previous, the one with the size k minus 1. So there is a very natural question, which is, can you define? Does there exist a family of symmetric functions indexed by something, and I'll get back to what in a second. Family of symmetric functions such that, so let me call them for now as lambda, where lambda is something that will specify, and then there's an arbitrary number of variables, y1, dot, 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 infinite number, as many as you like, so up to y, say, yeah, yk, say, but then any k n, such that when you specialize to the kth term, and you take the class inside, so yeah, let me just write it, s lambda of y1, yk, the kth, and then you take the class, so I don't know how to write this, you take well, yeah. You take the class inside the cohomology of the Grassmannian. This is exactly as our favorite Schubert class. And so the only question here is, this is not even a precise question because I haven't told you what the indexing parameter, so what is this lambda? So the idea is the following. We're going to think of Young diagrams, instead of being Young diagrams inside a box, as being free Young diagrams, free to live, and unbounded Young diagrams. So lambda here is an unbounded Young diagram, right? So if you prefer a petition, it's the same. So it's a Young diagram, but you don't care what the embedding box is. So for example, in the case of E1, I really want to think of this as just one box and not one box sitting inside a k by n rectangle, right? So free Young diagrams. Right. So you can see that this is going to work for E1, obviously. I already told you the answer. This is already a family which satisfies all these properties. And the claim is this always works. And there is a corresponding family of symmetric functions indexed by Young diagrams, which is called Schur functions. So the answer is yes, and they're called Schur functions. And sort of the geometric justification for why these things existed, I may want to postpone, and as I said, I may or may not have time to get back to it eventually. All right. But in a sense, either these polynomials there, or these symmetric functions, whatever, symmetric polynomials or symmetric functions are sort of the main factor of the, well, not this lecture yet, but the next lecture, let's say. All right, but before we proceed, I'm afraid I still have to do some hard work, which is this equivalent cohomology. So again, for the people here that are more like math oriented, this is all about spectral products. This is what we've done so far is like having an integral system and without having introduced spectral products. And we know that to do things like commutation of transform matrices and stuff like that, we need spectral products. So we need to work a little bit harder, and therefore we need equivalent cohomology. And it's a little less obvious because this is no more like just, it's not as intuitive, let's say, as just ordinary cohomology, but it's not that bad. As you'll see, morally speaking, it's going to be some kind of multi-parameter version of ordinary cohomology. In the same way that and you can introduce spectral parameters in an integral model and get some kind of multi-parameter integral model corresponding to it. The parameters being the inhomogeneities of the integrable system. Okay, so how do we introduce these extra parameters? Yeah, so first, again, I have to go in full generality. So in general, you're supposed to have a space, not just in our topological space, but a space on which some group X, and as usual, for me, X will be smooth, projective, complex algebraic, and G will be, let's just say, an algebraic group. In fact, very soon it'll be a torus, in fact, but yeah, let's just say a group for that. And you want to somehow define the cohomology that sort of knows about the action of G. So you don't want really just the cohomology of X, but the cohomology of X sort of mod G. And so the naive answer would be, okay, how about we just say, so we're going to define, this mysterious thing which I wanted to define, which is the equivalent cohomology, G equivalent cohomology of X. How about I define it to be just the cohomology of the orbits, right? The G orbits inside X. And then we know this is not a good idea for many reasons. But let's just say this works, but only if the G action is free. G acts freely on X. As soon as you have places where G doesn't act freely, you have, first you can see that the space will be very singular. You'll have, it will be like an orbifold. You'll have problems at the places where, for example, when you have this point, you'll have a very, very ugly singularity. So suddenly that would not be an algebraic variety. So suddenly from a point of view of algebraic geometry, this is very bad. But even from the point of topological point of view, this is not quite right. You're losing a lot of information, interesting information about what's going on, about the group action, by taking this kind of stupid, naive questions. And so, you open your favorite algebraic topology book, and you read what the recipe is to solve this problem. Here's how you so you want to somehow reduce to the case where the action is free, and that's not so bad because you say, how about suppose given so I'm very sketchy version of current cohomology. Suppose you're given a contractible space. So let me call it EG. Well, everybody calls it EG, not me. On which G acts freely. So the trick you're going to use, you're going to replace X with something which is homotopically equivalent to X, but on which it acts freely. So the idea is quite simple. You're going to say replace X with this thing, X cross EG divided by G. Well, I'm sure I had it better written in my slides. So you replace X with G. So in other words, what you're going to do is you say X cross EG now has a free action because it's already acting freely on EG. So now we can take the quotient and that's fine, right? So that's the general definition of H star G of X. So that works in any case. So you're okay. So as I said, this is all fine and abstract, but fortunately we're only ever going to deal with very easy cases where I can work out everything explicitly. So it's in a very important special case, which is a very non-free case. Is suppose x was actually a point. So you're taking just a point with, of course, trivial action, because the point, nothing can act on it. So in particular, so this is a very non-free case, h star g of a point. That's nothing but h star of pg over g, which is often denoted by bg, is classifying space. Okay, so even the equivalent homology of a point is non-trivial. Okay, so how about we work out the only example that we'll care about? And so in what follows, we'll always assume that G is just algebraic torus, complex torus. So something very explicitly, it would be something like C star to the power. No, not the same n. It'll be the same n. So might as well do the same letter. Right. So just a bunch of copies of the circle. So this is a circle for me. Again, this is you might say it's not exactly a circle, but it's a complex algebraic circle. It's the right? So this is clearly an algebraic group commutative. So the only non-trivial datum that we need is a contractible space on which G acts freely. So let's even do even simple. Let's start with n equals 1. Just one circle. Okay, so we need a space, preferably because I like something that doesn't look too far from being an algebraic variety. Let's say on which C star acts freely, and it's contractible. So we actually knew a bunch of spaces, by the way, on which C star acted. Remember when we discussed the Pn? So now it's not the same n. So let's say Pn for now, temporarily. Remember, we defined this as being something like Cn minus 0 divided by the action of C star. So we had a candidate for something on which C star acts, which was just a bunch of n complex numbers. And the quotient was actually something nice that we know, but unfortunately this cannot be right. So this is not contractible. And in fact, just for the record, let me remind you that h star of the quotient, which is just C star was given by z of x divided by, so I keep changing my mind, so here is Pn minus 1, sorry about that, divided by the ideal generated by xn. So in particular, you see that this ring depends explicitly on n, so it better be that, since we want an answer that's sort of universal, it better be that this is not the correct answer. And indeed, this is not contractible, this has non-trivial homology in dimension n. Well, 2n, sorry, real dimension 2n. But you see, the point is precisely, since the obstruction is only in dimension n, how about we take the limit n goes to infinity, right? So this is a physics style, right? Don't ask me what this means exactly, but, well, no, you can ask me. So the answer will be simply, sequences of variables z1, zn, dot, 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 as many, an infinite number of, countably infinite number of variables, let's say, such that the number of the non-zero variables is non-zero, suddenly, because I don't want this to be right at 0, but also non-infinite. That's a reasonable limit, of n goes to infinity. That I claim is contractible. And it still has a C star action, which is just, again, multiplication by, so it still has the same action of C star. And then you can ask what is the cohomology of this thing. So I don't have a name for this. So let me just call it C infinity minus 0 divided by C star. And morally speaking, it has to be the limit when n goes to infinity of this thing. But this ideal gets smaller and smaller, right? So at the limit, it's just 0 of that, right? It's the limit of this thing when n goes to infinity morally. Again, physics level of rigor. And now you'll note the amusing thing that this is actually already an infinite dimensional. An infinite. An infinite rank module of over 0, an infinite. An infinite rank Z module because we lost the finiteness, in the quotient. So This is it. This is exactly H star, C star of the point. Now let's compare to what we had before. We had just H star of the point. The cohomology of the point was just, well, the class of the point, which was Z, right? So the difference between here and here is we have an extra parameter X. This is our spectral, so this is called equivalent parameter, but again, this is the same as spectral parameter in these guys. All right.
Is one of these things EG in the thing you just described?
Right, so.
Which is EG in this example?
Yes, so this is EG, EC star. Yeah? All right. So let me say a few more things about generalities before we go on. Right, so first you may tell me, okay, now you explained to us just how to find the cohomology of a point, but what about an actual space? You know, suppose you actually you're given a space with, oh no, first let me do C star to the power n, sorry. Obvious generalizations that I leave in exercise. If you do this for H star of C star to the power n of a point, you'll get this time Z of x1, xn. So if you do it with a torus of dimension n, basically you have one variable for each direction in the torus. And the way you want to think about it slightly more abstractly is this is nothing but, so let me call this, so tori I will always call T and not G. So more abstractly you can think about it this way. You see, so each of these variables, you should think of it as a weight of your torus. So you see, you know, when you do representation theory of your torus, you know, every irreducible representation is given by a certain weight, which is given by a certain lattice, right? So in other words, this T star here is the lattice of weights by definition. This is my this lattice of weights of T, which means in other words, the characters, you know, morphisms. So in other words, this is a sim of the set of characters, right? Chi goes from T to C group morphisms. Right? So when you take the characters of a torus, they form a lattice. You take the sim of that. So in other words, here the lattice is basically the linear combinations, you know, like sum of ni, xi, where I goes from 1 to n. This is by definition, okay, maybe not ni, maybe. This is what I call the lattice of weights. And then I take the sim means instead of taking just linear combinations, I take arbitrary polynomials, right? So if you don't understand this, it doesn't really matter. I mean, explicitly, this is all there is. It's a polynomial ring in n variables, but there's a kind of more abstract way of thinking about it in terms of the lattice of weights of the torus. All right, we probably won't need that, but it's just, yeah. So I told you now how to compute the cohomology of a point, which is not terribly exciting. You may want to we might want to go a little bit further, but there's actually something very nice that happens then. And the very nice thing is as follows. Consider now the so whenever you have a space X with a now T action, you can always send this point. Let's send this. Yeah, right. Sorry, I knew I had forgotten to say something. Yeah. So obviously now we have a notion of pullback, and in principle push forward as well. Yeah. So that's something I probably should say first. So since effectively all we're dealing with is ordinary cohomology in these guys, all the usual constructions apply. In particular, you have pullbacks and push forwards as soon as you have maps which are equivalent. So for T equivalent maps which, in other words, respect the torus action. Right? So it's kind of morally obvious that there should be, again, just pullbacks and push forward. And the first application we have is the following. Suppose you have a space X with a T action, you can always project it, as usual, to a point, and suddenly that map will be equivalent, because the action here is the trivial action, and therefore you have a pullback, which is the morphism of ring from H star t of a point to H star t of x. Yeah? And so that's pretty good, because that tells you, so this of course we know, this is in our case just z of x1 xn. And that means that this thing here is basically, is that really what I wanted to say? Kind of losing track of what I'm trying to say. Yes, so anyway, yes, so the point was that, yes, so, yeah, let me write it before. When you have a map of a ring into another ring, I guess that makes, well, that makes it in particular a module over the source ring. Is that the correct statement that I said? For a second I got confused in my, right? So this implies this thing. So you see that's actually very nice, because you see it's not like these spaces are completely wild. They're just basically modules over the class of a point. So in other words, that's why all the time before I kept saying Z module, which is a bit of a silly thing, because the Z module is a group. But you see here, this is exactly the analog here. Instead of having Z modules, we have Z of x1, xn modules, basically. So things which are not that wild. Yeah? So, so what more should I say about generalities? Yeah, right. So in particular, there's another natural map that I wanted to mention. If you look at this space EG cross X over G, so what is this space? So EG was the space with the free G action. So basically you should think of it as a lot of little copies of G floating around. And what you've done is that you multiply by X and then you divide it by G. So secretly what you've done is you had all these little copies of G which you've replaced with little copies of X, basically. Right? I don't know if that makes any sense. I'm sure there's a more fancy way of saying this thing. No, sorry, no, don't. Yeah, I'm just checking if I have notes on this subject to say this more formally. Yeah. Anyway, so the point is, in particular, you have. Yeah. So let me just give the very simple version. In particular, there are many little copies of X floating around inside this thing, and it doesn't really matter which one. This is just the fiber of this map. Is this correct? I should probably have thought of this before coming here. But anyway, so the point is, you always have this embedding of. Yes, correct. Exactly. So you always have an embedding like this. Let me call it I, which means you have a pullback map. So you have a pullback map from H star of EG cross X over G to H star of X. But of course, what is this thing? This thing is nothing but, by definition, H star G of X. So what is the point of this whole argument? Is just to say that there's always a way of forgetting about equivalence. This is the forgetful map. Yeah. So in other words, exactly in the same way as in integrable systems, when you can introduce homogeneity into your systems, and then in the end of the day take them all equal to 0. This is exactly what we're saying here. So this is, by the way, is not always, but often, let's say, subjective. I'm not going to say why. And certainly in the case that we have, it will always be subjective. And morally speaking, this map is just saying set all parameters, whatever they call xi to 0. All right. So if you ignore all these parameters, you forget about z of x1 and xn, you get back to z, and this is like getting back to non-equivalent homology. All right, this is not such a great explanation, but I think morally the picture is clear. If you really want to, you can always get rid of this equivalence, but it will be useful for our purposes. All right, so enough with abstract things. Let's just do our favorite examples, probably. Or did I have something else in mind? No. First, I want to say one more general word about homology. So the way I presented cohomology was basically via homology. I said, cohomology, I can't be bothered defining it properly, so I'm going to define homology, which is easier, and that's the end of the story. So what about here? Can we define everything in terms of homology? Yeah, pretty much. So the idea is, every T invariant subvariety of X. And here, let me emphasize the only difference with the first talk is that every invariant subvariety, T invariant subvariety of X, has a fundamental class, has a class, fundamental class, right? So you can still think of your cohomology classes in a sort of homological setting, but they only correspond to subvarieties which are invariant on the action of the torus. So that's very geometric. You see, that means as soon as you have your space X, the first thing you want to think about is what are the T invariant subspaces, and these will give you naturally classes in equivalent cohomology. And as usual, they will be graded by codimension. So the degree, as usual, well, nothing else has changed. There is a grading, and the degree of y is up to a factor of 2. As usual, the codimension of y. All right. So everything is pretty much the same as before, and yes, and we have the same theorem that if, so fact as before, if there exists a T invariant cell decomposition. Again, it's the same story as before, cell decomposition of X into, as usual, closed algebraic subvarieties, T invariant. Then of course, then H star T of X is a free H star T of the point module, which is generated by classes of closures. Yeah, classes of closures. So everything is the same, except now you have to. And yeah, and by the way, with reasonable assumptions, very mild assumptions on your space, there always exists such a, for a torus, only for a torus. There usually always exists such an T invariant cell decomposition if you already had a cell decomposition, so it's not such a strong additional assumption. So everything looks pretty nice. So let's do the example of P1, and we'll see where things get hairy. Because eventually there'll be some complications, and it can't be that easy. So let's do our favorite P1. So P1, remember, was the sphere, and I thought about it as maybe being C union infinity, which is in fact a particular cell decomposition of it. And then now I want to add an action, so I say C star acts naturally by Z goes to TZ, and of course infinity just goes to infinity, right? So infinity is not changed. So this is your T star action. So morally, so what happens? So there are now 2 points which are special. There's 0 and infinity. Yeah, this is going to be, as usual, very trivial, but remember that essentially everything, almost everything we'll be able to do at the level of P1. So if we understand this example, we can do almost everything. So let's understand this example. Yeah, so there are two fixed points, which are 0 and infinity. And that's it. Everybody else is, there are no other invariant subvarieties except the whole space itself, obviously. So in other words, at our disposal, we only have 3 classes, 0, infinity, and P1, but really remember that you have to pick one for a cell decomposition, right? So you have to pick one out of 0 and infinity, and that forms a cell decomposition. You're not going to take both at once, right? So you have to pick one, which means your equivalent cohomology of P1. Yeah, so it's a free module of. So in other words, yeah, it's a free module of rank 2. So it's just H star. Ah, yeah, right. So and we even know what H star of a point is. So it's just Z of X plus Z of X. Yeah. Where careful now that the X here is the equivalence parameter, right? And this is the class of you could choose 0 here, and I say P1 here, or you could choose infinity. That would be a different basis. So yeah. So as a module, this is completely trivial. This is the end of the story. All we've done is added parameter X, and nothing else has changed compared to the previous time. Of course, the problem is when well, there are 2 problems. The first thing is, suppose I choose the basis 0 and P1, how about the class of infinity? It should be expressible as a combination of these classes, right? Because it has to be, and we can even be a little bit more careful, because, so the degree of this thing is 0, the degree of this thing is 2. Remember that the degree of x is also 2. Now the additional subtlety, so the x here secretly also has a degree. So what can infinity be? Well, basically it has to be of degree 2 as well. So the only thing it can be is a linear combination of 0 and x. Yeah, these are the only degree 2 elements in there. And also we know that in the non-equivalently, all points are equal. So non-equivalently, infinity equals 0. And non-equivalently means setting x equal to 0. So it better be that this is the case, right? And you still have this coefficient, which at this stage we cannot determine.
You said they have to be degree 2, though. 0 is degree 0.
Sorry.
You need B2 plus x.
I screwed up here as a degree. Yeah, sorry. Yeah, so so this is graded by codimension, sorry, not by dimension. So the whole space is of degree 0, and 0, the point 0, maybe I should have pointed, yeah, is of degree 2. Sorry, my mistake. So everything here is of a degree 2. 2, 2, 2. And beta is just an integer in principle, which we can't determine at this stage, unfortunately. Of course, we know that beta equals 1 eventually, but I can't show it to you without using some more artillery. And the same problem arises in a slightly different way, which is when you try to understand now the ring structure. Because remember, this is not just a module, it's also a ring, right? So we should be able to take products. And again, trouble arises because right. So what about doing things? So of course, yeah, the class of P1 is still the unit of the ring for stupid reasons, so that's not going to change. But what about, for example, taking the class of 0 and squaring it? And non-equivalently, we remember that the result had to be 0 because the class of a point, you take 2 generic points on your sphere, and they don't intersect. So non-equivalently, it used to be 0. But here a problem arises. We can't move things around anymore. Remember, this is the problem that I discussed before, that you want to take representatives in such a way that intersection is transverse, but once you have a group acting, things are much more rigid. There's only one fixed point. 0 is just 0. You can't move it around a little bit and say, okay, I'm going to intersect 0 with some other point. So it's here in principle, you don't know how to compute this, right? The only thing you know how to compute, by the way, is 0 times infinity. Because this is most definitely transverse, because these 2 points don't intersect as they should. Because on the sphere, you take 2 points, they shouldn't intersect. So this is most definitely 0. But that doesn't help, because you see that if you replace, you find that, so maybe we should give a name to the generator. Let me just call y to be 0. This writes something like y times y plus beta x equals 0. So you know that y is going to satisfy some kind of quadratic equation, but you don't know which one, right? Remember that it used to be that, so of course, I know the answer, and I can tell you, at the end of the day, beta is going to be equal to 1, but at this stage, we cannot fix what is the ideal of equations of, so in other words, h star c star of P1 is going to be, of course, at the end of the day, it's going to be z of xy divided by this mysterious equation, y times y plus beta x. But we don't know at this stage how to fix beta, right? And you see, you have 2 generators which play kind of weirdly asymmetric roles. There's y, which is the class of, say, a point, but there's x, which is the equivalent proper, and they don't obviously play the same role. Of course, there's some way of thinking of them on equal footing, but I may or may not get there today, depending. All right. Right. So now let's get back. So yeah, okay. So we're supposed to do the same. Yeah, just ignore what's on the screen. It's just, I'm quickly looking at my notes. So in principle, now we want to play the same game with the Grassmannian. And there are a few things I need to explain. So first, what is the group action? So let's get back to the Grassmannian. GRKN. So remember that there is naturally a group GLN acting on this, which is just when you have a subspace inside Cn, you just rotate it using an element of GLN. But inside, so GLN is sort of too big for us. You could consider GLN equivalent cohomology. That's not a completely stupid thing to do, but we're not going to do that. So instead, we're going to say inside GLN there is a torus, and that's the Cartan torus, right? So it's just a diagonal. These are just diagonal matrices, let's say, in this diagonal matrices, invertible matrices. Right? So, and it's most definitely dimension n. Yeah. So that's so that's what I'm going to consider. I'm going to try to study H star, C star, and of GRK. That's going to be our. In many ways, this is going to be the central object of everything that follows, all the lectures that follow. And that's going to be your. Yeah. And so we have to say something about it. Okay. So. Okay. What do I want to say about it? Yeah. Right. So we want to apply the theory that we had before, which was we want to say the question is, can we have a T invariant? That comes a crucial point. We want to find it. So T here is a C star n. Yeah. So maybe I should just call once and for all T, because it's not like it's going to change anything. So the question is does this thing have a T invariant cell decomposition? Right? If there is, then we're in business. We can just apply the big theorem that I had before. And as I told you, this is not so hard to do. It's not going to be very hard. And in fact, I'll immediately reuse our favorite Schubert classes. So how is it going to work? So we used to have a cell decomposition. In fact, we had plenty of cell decompositions. Because remember, recall, given a flag, which was just these subspaces like we had on the computer screen, you know, V1, 0, V1, V2, dot, 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 Vn, which is Cn, with dimension Vi, which is I. Vector spaces, we define a cell decomposition by taking the fibers of the map which computes the dimension of the I intersect your space V for all I 1, 2, well 0 to n. Yeah, well you can call this V zero. So the question is there any chance that these, and remember these cells were called Schubert cells. Now the question is, are these Schubert cells T invariant, right? If they are, we win. And the question, and the answer is obviously it depends on what you choose as a flag. You know, if your flag, you know, these Schubert cells are T invariant if and only if the flag itself is. And by that I mean every element of the flag. So yeah, if and only if the I is T invariant. Why? Well, you can see that this identity immediately, you know, if Vi is T invariant, then you can act. It costs nothing to act with the torus on V because you can absorb it in the Vi, right? I think this is kind of obvious. If you're no, does it make any sense? So the Schubert cells, which means the fiber of this match, are T invariant if only if the actual flag, so that means the Vi, are T invariant, right? Because if you rotate an element, if you take TV, then the dimension of TV intersect Vi is nothing but the dimension of TV intersect T inverse Vi. And if Vi is invariant, you can forget this, and you get back to the original one. Yeah. So it's just obvious covariance of the thing. So now the question is, how do you build it into T invariant flag? So this is a very basic, geometric question. So if you're given, so let's assume again that in kind of in coordinates that these this T is just diagonal matrices. So let's say we have already given ourselves a sort of standard basis. How do we build a T invariant flag? And incidentally, anybody care to guess how many such flags there are? No? No guess? Well, yes, thank you. Yeah, in fact, there are exactly n factorial such n factorial. And so this is very important for me, so let me write it explicitly. So it's almost a trivial word, but it's important. There are n factorial T invariant flags. And so if you use the standard basis, the way you do it is simply you arbitrarily add some. So you have to use basically. So you have your standard basis whatever ei I goes 1 to n of Cn, and you have to create your flag by just adding successive vectors inside your basis. So vi is going to be some subset.
You choose v1, and you have n ways to choose v1.
Right, exactly.
Have n times n minus 1.
Correct. Exactly. So it's going to be the span of some EW in general W1, EW I, where W is some permutation. Yeah? And so this is already secretly we have the R matrix here, because you see there are some permutations going on, there's some bound group actions, and there's an R matrix going on. So the R matrix has everything to do with the change of basis from corresponding to different choices of flag. So that will be the key message of the next lecture. So I can already reveal to you. It's a great secret.
So anytime you have n factorials, you assume you have R matrix behind.
Well, you have a bound group action. So each time, well, even that's a little bit too crude. That's not literally like that, but yeah. So anyway, yeah. So you have many choices in principle. And these choices that you see are in one-to-one correspondence with in one-to-one correspondence with basically I like to think of it as orderings of the alphabet x1 xn, because essentially what you're doing, each letter xi secretly is telling you about the torus action in the direction of ei, so permuting these letters is the same as choosing different flags. So that's a useful way to think about things. So, yeah. All right. Okay, so once you've chosen such a flag, you're done. You have some T invariant Schubert classes, and therefore you have the theorem that, as usual, now given such a T invariant flag, everything works fine. T flag H star T of the Grassmannian. It's just basically a free Z of x1 xn module, if you like. Well, to the power n choose k, let's say. Let me write it in a short notation. So, free module of the dimension n choose k. N choose k. Did I write it correctly this time? I never know which one is k. Anyway, I think it's correct. N choose k. Yeah.
Bigger is on the top.
Yeah. No, it's not very well written, but yeah. Yeah. But in principle, you do have those n factorial choices. Right. So there are two more things I want to say. So first, I want to talk about the pairing again, and then I want to talk about the presentation. Because of course I'm going to give you a presentation of it. So this is a description as a module, but I want to approach the description as a ring. So that will follow. But before I do that, let me talk again about the pairing, because the pairing is sort of important, and it will also appear naturally in integrable systems. So that's why all the ingredients that I'm talking about, that's more or less a reason why I introduced them. I should probably have not erased our favorite example of P1, because we had not quite finished. We were still missing a coefficient somewhere. I'll leave it here. Yeah, so let's talk about the pairing. So what do I want to say about pairing? I just realized I have no idea. I did write here that I want to say something about the pairing. But I don't know what, so maybe we'll postpone the pairing until we remember what I wanted to say. Probably not so important for pairing. I have a big, I don't know, I'm sure there's something deep to say, but okay, we'll come back to the pairing later. Yeah, let me just talk about the presentation. Okay, Sorry, bad preparation. Yeah, okay, so let's just talk about how to present this ring. So of course, there's an answer, which I can just write to you. And there, in here, it's really better to use those symmetric polynomials rather than elementary symmetric functions, because the elementary symmetric functions themselves do not have any geometric meaning. So let me just give you the answer. So h dot t grkn as a ring. So what is it going to be? So clearly, it's going to involve the same variables that we had before, y1, yk. But then we also have to have all these extra parameters, x1, xn, which are the equivalent parameters. And then we're going to have some ideal, right? Which is and also I want to say here, I want to add, okay, so this is getting bad, but I want to add sk. So symmetric polynomials in k variables, and then you have n extra variables, all of which have degree of yi equals degree of xi equals, say, 2. And so the question is, what is the ideal? And you know. So the simplest way, which mimics exactly the way that I wrote it before, is to now introduce this thing. Say I equals 1 to n, product of 1 plus txi over product from I equals 1 to k of 1 plus tyy, yi. And then I say this thing is a polynomial of degree. It's the same argument. Polynomial of degree, what is it? N minus k in t. So any higher order terms vanish. It's not too bad, right? The proof is exactly the same, by the way. And just for the record, let me write that the proof involves just using exact sequences of equivalent vector bundles, whatever equivalent vector bundles are. But if you believe that there is such a thing, then there is an exact sequence of equivalent vector bundles, which I'm not going to. So essentially the same argument works, except that make everything equivalent. And in particular, you see that the numerator is nothing but the total chunk class of the trivial vector bundle, which was trivial, of course, non-equivalently, but still has some non-trivial equivalent structure, basically. But otherwise, it's the exact same argument. Right. So this is the total chunk class of I guess this guy. This is this guy, and the other side is this guy. So it's the same argument. And again, this is nothing but the TQ relation in this guy. So eventually, I want to get back to that. In many ways, yeah, this is our favorite TQ relation of integral systems. All right. Yeah. So let's check, for example, P1. No, let's do Pn directly. Yes, let's do. So let's when you know that Pn minus 1. So what happens? So here it's pretty easy. You have only so you can just compute by brute force. Just expand this. After all, it's not so hard, right? You only have 1 over 1 plus ty in the denominator. But let's not do that because that's a bit lame. So let's try to be a little bit more clever. So and let's do something that will actually work really for any Grossmanian in some sense, the argument. But anyway, let me do it here. So we want to say that this polynomial is of degree n minus 1, which means in particular the term of degree Tn of this thing should be 0. Yeah, Tn term of. So we want to compute the Tn term of this thing. And we know, of course, that it's going to be some polynomial in y and x1 and xn. But let's say in particular polynomial in y. And we know from the structure here that it's going to be a polynomial of degree. So this thing is going to be a polynomial of degree, let me get it right, n in y, right? Because you're going to expand, and the most y's you can get by expanding is 1 to the power n, if you only look at the p to the nth term. Do you agree with this? But furthermore, you see that if you compute p of xi, that means you substitute y equals xi, there is a nice cancellation that happens, and you get a polynomial of degree n minus 1, which means it has no Tn term. So that means this polynomial vanishes at every, yeah? So this is yeah. Because then you have cancellation between numerator and denominator, and therefore there is no T to the nth term, right? And therefore, a polynomial which has n roots and in degree n, there's not so many of them. And fixing the normalization, I'm not going to bother doing that. There's going to be some constant which I can't be bothered, like sine probably, but up to something, it's going to be product of y minus xi. Yeah. And so we conclude that the h star t of n minus 1 is just z of y x1 xn divided by product of y minus xi. And so this is a pretty, the ideal generated by this thing. Yeah, and then you have to check that all the higher order terms also vanish, but this is fairly easy to check. So you see, this is kind of nice, because remember when we computed the non-equivalent case, we had just here, we had just yn. And yn has been replaced with a polynomial which has distinct roots, these xi's. So this is very important. We used to have a nilpotent algebra where y to the nth equals 0, and now we have essentially a semi-simple algebra where y satisfies a polynomial with simple roots. So that's of course at the technical level, that's really why equivalence is so nice, because it's a. But anyway, I should also point out a little remark is that this doesn't obviously match with what I said about P1. So let's just now do n equals 2, even more elementary. Then we find here z of y x1 x2 divided by y minus x1 y minus x2. Ideal. And here it doesn't quite look the same. And the reason is pretty stupid. It's because here the torus acting was actually Cn, C star n, which is in this case C star squared. So here I'm making a torus of dimension 2 act, and here I had only a torus of dimension 1. So there seems to be a little bit of a mismatch. But this mismatch is trivial because, yeah. So maybe I should have made this remark from the very beginning. There's always a subtorus, a subcircle. Yeah. So I guess the remark should really be for general GRKN. In fact, since the pairing has been dropped, then you make the remark here. In general, when you make C star n act on GRKN, there's always a circle inside here acting trivially. And that's the circle corresponding to scaling, because when you have a vector space, it's invariant by scaling, right? So this is the scaling part. So in other words, matrices which are proportional to the identity. And therefore, the torus that's really acting is not C star to the nth, it's actually C star to the nth divided by C star, which is non-canonically isomorphic to C star to the n minus 1. So you only have n minus 1 parameters. And so what I did in the case of P1, I've already subtracted that stupid torus by hand. And what it means in practice is that when you, so that's the continuation of the remark. In practice, that means when you compute the class of anything, it's only ever going to be a function of the difference function of xi minus xj, of the difference of equivalent parameters. Because you see, you're going to the dual, so you're taking the quotient of the torus. That means in terms of the characters, you're taking a subweight lattice, right? So it's the weight lattice which only depends on xi minus xj. It's the usual story of like GLN versus PGLN or whatever. And so what happens is really here. You see, if you now perform the substitution, y prime equals, say, y minus x1, so there is some arbitrariness in the substitution, which corresponds to the arbitrariness in rewriting the quotient as C star. But suppose you write y prime equals y minus x1, then this becomes simply y prime times y prime, plus x1 minus x2. And if you now set x to be x1 minus x2, which is the you get back to this equation with beta equals 1. So everything is fine. It's just a minor subtlety on the. But you see, these parameters are much more natural. In other words, to simplify here, it's in other words, yes, they're redundant, but it's nice to keep them redundant anyway. Even, yeah. Okay. So what else do I want to say today before we finish? I should finish at 7. Yeah.
Yeah. More or less. More or less.
Yeah.
Plus minus 5 minutes. Okay.
Yeah. So let me give you, so I haven't, so in principle, of course, the next stage is to say, so, well, we want to compute in this presentation the classes of, yeah, so I'll give later another justification, by the way, of the value of this beta, and this will have to do with the correct localization. So the big next subject eventually will be localization, but that will be probably for next time. And so now probably I just want to end with a few examples and remarks, and maybe finally say something intelligent about the pairing. Right, so example. So in principle, each time now you have so let's choose the most obvious. Let's choose the flag to be span of E1, EI, the sort of obvious choice once you've fixed an ordered basis of your space. That gives you Schubert classes, and so that means these Schubert classes should be expressible in this presentation, right? So for example, I should be able to tell you what the class now of the equivalent class of the one box, for example, equivalence. Let me insist by putting a little t. So what is this thing? So we already know that non-equivalently it used to be just the elementary symmetry, the sum of coordinates. So it used to be just y1 plus dot 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 plus yk. But here, of course, it's going to have a. So this cannot be just like this. Oh yeah, I see. Oops. Yeah. Okay. No. Never mind. Let me. Right. And the contribution is going to be minus x1 minus dot 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 minus xk.
You have x and x's.
Exactly. That's exactly my point. So you see, this seems very strange because you have n x's and I only took k of them. But that's precisely because we made this choice. Of course, if we had chosen another permutation here, you'd get another subset of the x's, right? So you can see how this thing is much less symmetric because you had to make this choice of your n factorial choices, right? So in particular, this is not symmetric in the x's, right? And this will be important. In fact, once again, the ordering of the alphabet, or in other words, the exchange of the x's will be essentially what leads us to the matrix. So it's important here. And so on. So you could write more examples, but of course, at the end of this class, there will be a general formula for all of these. So I guess okay. So I guess I'll say at least a few words about what's going to come next, which is localization. So this is all fine, but this is too complicated. We can't. It's very hard to do actual computations, with these rings if you don't have a bit of a few tools. And so the tool we're going to use is localization. So first, what do I mean by localization? So this is in the sense of algebraic geometry, which means we're allowing ourselves to invert things. And from a physics point of view, this is very natural. I'm just saying, yeah, well, these parameters xi, I really morally these xi's, I want to think of them as actual numbers. So I should be able to, for example, maybe take their inverse or something. And of course, you're not allowed to do this because this is, a polynomial ring. So how about we allow ourselves to do that? So this is exactly, and the most brutal form of localization is, say, we're going to replace a star t of a point by its fraction field. Right? We're going to say, instead of working with cohomology rings, we're going to work with localized cohomology rings, which are just, let's say, in the most brutal form, I allow everything to be invertible, while every non-zero element to be non-invertible. So in this case, that would be like Q of Z1, Z, and so remember, we used to have polynomial arbitrary fractions in the variables Zi. It's a bit of overkill, by the way, because we won't need every denominator, but might as well, who cares? So the advantage is this thing, of course, is a field. So now instead of having like modules, we have vector spaces, which I'm much happier with. You can forget about all issues of torsion, in particular, and things are nice and easy. And so by the way, I don't know, maybe the specialist can help me, but I have not found a notation for localized cohomology rings. So let me just introduce arbitrarily a notation. Let me say that I denote H tilde star t of x to be exactly what you imagine, which means the ordinary equivalent cohomology, but in which I tensor with a fraction field. So maybe I'm going to give it a name because it's going to be annoying, so I'm just called F. So tensor over H bar T of a point of F. So morally speaking, that means I allow myself to invert arbitrary, take arbitrary rational fractions of the parameters. Sorry, they're not called Z, they're called X. My mistake. Sorry. This is, by the way, not the Y's. You better not touch the Y's. The Y's are better stay as they are, but only the X's, right? And so this will induce quite a few simplifications, and in particular, the fixed points will play a key role. But maybe I think this is the perfect time to stop. So yeah, and eventually we'll have some discussion about fixed points. Okay, but that'll be next time. All right.
And the R matrices will appear.
All right. Okay. Maybe I should give you a preview. Yes. Good point. And also the next time we'll study. So what happens is now we have classes S indexed by I, but also secretly indexed by permutation, right? If you're right. Well, I is some subset in one n, cardinality K, and W is a permutation, basically. Yeah. So and of course.